Now, let's have a summary of process in solving non-exact equation. This equation again pertains to this form here, m of xy dx plus n of xy dy be equal to 0. But we're not able to establish this criteria for exact situations. You have here the partial derivative of m with respect to y is actually not equal to the partial derivative of n with respect to x. Because if it is equal, then we use the process of solving exact equations. Now, if this is not, again, equal, so we are going to use the process of solving non-exact equation. And actually, we had to use the integrating factor for the specific situation discussed in the previous video. So how do we solve now our, how do we write here or outline the process? So we will start here, okay? So we have here the steps. Number one is, of course, this might not be needed because we are sure it to be non-exact, but just to be sure, let's verify that the partial derivative of m with respect to y is not equal to the partial derivative of your n with respect to x. Of course, again, if this is true, then basically we know that this is actually a non-exact equation. But I'm just writing it that here so that I can actually verify the complete process. Okay. Now the second one, let's call it 1. The second step pertains to, since we now sure that it's a non-exact equation, it's now part of finding the integrating factor. Okay? Just a short review, the integrating factor will help us identify a certain factor to be multiplied on all the terms here so that we can proceed to the process of solving exact solution from a non-exact equation. Okay? So anyway, let's start here. Let's verify or solve, because we are now sure it's a non-exact. Solve 1 over your function of n times, okay, the partial derivative of m with respect to y minus the partial derivative of your n with respect to x. We know this to be not 0 because they are not equal as verified here. So we have a factor for that. Okay. So if this is actually equal to a certain function just expressed in a singular variable x, then it's already okay. Okay. If not, okay, or you solve here the other one, the ratio of 1 over m times the same, okay, expression. If this fits f of y, a function of y, then we use that one here. So basically in step 2, you will decide which is possible, or even if these two are possible, which of this you will be using, because the third step, the integrating factor now, will be dependent on which you will be using here. Okay? So basically step 2 together with step 3 is for the integrating factor. But basically for step 3, you have here the integrating factor after you have decided which to use. If you're going to use f of x in step 2, your integrating factor is mu of x equal to e to the power of the integral of f of x dx. That is, again, if we have established that this entire function or expression is equal to a function of x. Okay? But if it's not, our f of y will be equivalent to our mu of y, e to the power of negative of your f of y dy. Okay? So again, these two are dependent on your step 2. But basically, as mentioned, step 2 and step 3 are on the integrating factor needed for your the solution of your non-exact equation. Okay? So, let's proceed to step 4. Step 4 now, which you will be using here, so you multiply, okay, your mu on both sides. Hence, from this form here, original form, you will have this form here, mu of your m dx plus your mu of your n dy is equal to mu times 0, or basically you're going to multiply that, you will simply get 0. I'm just using here mu instead of mu of y or mu of x because, again, it depends on which integrating factor you're using. So just make sure that if you're going to use here mu of x, this should also be mu of x. It should be on the same factor is multiplied on both sides. Okay, so that is our fourth step. So I'm just simply writing that because it's up to you whether it's mu of x or mu of y. Then finally, for your fifth step here, you solve this equation using the exact method. Okay. I'm not going to specify here the steps for solving the exact method, but it actually uses a certain process as well. Okay, and then later on, a certain f of xy will appear, and then you have either g of x or g of y. Please try to review the video for the process of the exact method, because the fifth step is just equivalent to that step of finding exact the solution for exact equation. Because once you are going to multiply here, this one here, with the integrating factor, you are assured now that uh, from the non-exact, let me label here, this is a non-exact differential equation. From this, you will be sure now that it is already an exact differential equation once you multiply your integrating factor on both sides. Hence, that's why you use the exact method for the step 5. We will have some examples as to this, especially in the verification on whether the given equation is a exact or a non-exact, and later on, if it's non-exact, we'll be using these methods to solve for the solution. Thank you very much for watching.